Hello everyone, welcome to this learning video. I am Shubham from MSc Chemistry first year. This video is specially designed for visually impaired students. Inorganic Chemistry, Unit 1, Metal Ligand Bonding. Limitations of valence bond theory. It could not explain the nature of ligand, strong and weak. It could not explain why pairing of electrons occurs in presence of strong ligands. Third point, it could not explain the color and electronic spectra of some complexes. It could not explain the structure of CuNH3 2 positive ions. It could not explain why experimental value of magnetic moment is greater than calculated in some complexes. It could not explain reaction rates and mechanism of reaction of complexes. So, to overcome the limitations, new theory was introduced, which was crystal field theory. Valence bond theory is useful to visualize the bonding in complexes but fails to explain the nature of ligands, color, spectra, high spin, low spin, stability of complexes, etc. So, Bethe and von Vleck proposed a crystal field theory. This theory was applied to ionic crystal and called crystal field theory. Assumptions. Ionic ligands such as Cl negative, OH negative are regarded as negative point charges, and neutral ligands such as H2O and NH3 are regarded as point dipoles. So the interaction between metal and neutral ligands is like shown in the diagram. Metal ligand bonding is not covalent, so no overlapping of orbitals. This is purely electrostatic in nature. Two type of interactions: attraction between metal and negatively charged ligand, repulsion between lone pair of electrons ligands and electron of d orbital of metal cations. The 5d orbitals in a free metal ion are degenerate. When complex is formed, the electric field of ligand destroy the degeneracy of orbitals, and having high energy are those which lying in the direction of ligands, and those which are lying away from the ligand have low energy. So splitting occurs. This is called crystal field splitting. Shapes of d orbitals. There are 6 d orbitals having 4 lobes. They are dxy, dyz, dzx, dx square minus y square, dz square minus x square, and dz square minus y square. But dz square is taken as linear combination of dz square minus x square and dz square minus y square. Hence, there are 5 orbitals which have shape like shown in the diagram: dxy, dyz, and dzx. These 3 orbitals lies between the axes. Dx square minus y square and dz square. These 2 orbitals lies on the axis. Crystal field splitting in octahedral complexes. In a free metal cation, all the 5 d orbitals are degenerate. In an octahedral complex, Ml6 and positive, the metal cation is placed at the center of octahedron and 6 ligands are at 6 corners. These 6 corners are directed along the Cartesian coordinate along x, y, z axis. Octahedral complexes are in the shape of an octahedron where metal cation Mn positive is between the 6 ligands arranged as shown in the diagram. When all the 6 ligands are at infinite distance from metal cation, the 5d orbitals of free metal cation will not be affected by ligand electrostatic field and will remain degenerate. When ligand move towards the metal cation, there are 2 electrostatic forces. One is attraction between metal cation and ligand, and second is electrostatic repulsion between d electron of metal and lone pair of electron of ligands. Greater the forces of attraction between metal cation and ligand will be more closer to metal cation, and ligand will be more closer to metal cation, hence more will be repulsion between metal d electron and lone pair. Greater the forces of repulsion, higher will be the potential energy. In octahedral complexes, the spherically symmetric field is never obtained, so the 2 orbitals point directly towards the ligands and the 3 orbitals point not directly, but between the path of approaching ligands. So dx square minus y square and dz square will be more strongly repelled, and dxy, dyz, dzx orbitals. So energy of dx square minus dz square orbital will be raised, and that of three orbitals which lie far away from ligands will be decreased relatively to hypothetical energy state. This diagram shows the octahedral crystal field splitting. Firstly, there are 5 degenerate d orbitals in free state. When ligand approaches to metal, then their energy increases, and this is their average energy. And when they interact with metal, they split into two sets, Eg and T2g, where T2g is lower in energy and Eg is higher in energy. T2g is referred as dxy, dyz, dzx orbitals, and Eg is referred as dx square minus y square and dz square orbitals. Total energy difference between these two is 10 dq. So this is the crystal field splitting in octahedral field. So the set of dx square minus y square and dz square orbital is referred as Eg set, which is doubly degenerate, and the set of dxy, dyz, dzx is referred as T2g set, which is triply degenerate. The separation of 5d orbitals of metal cation in two sets of orbital which arise from octahedral field is measured in terms of parameter del O or 10 dq. Since energy barycenter is constant, the decrease in energy of T2g orbital stability, the complex by 0.4 del O, and increase in energy of Eg orbital destabilize complex by 0.6 del O. Crystal field splitting in tetrahedral complexes. A regular tetrahedral geometry is obtained when a metal cation or atom is placed at the center of cube and four ligands occupy the alternate corners of the cube, as shown in this diagram. The XYZ axes are passed through the center of faces of cube. None of the ligand approach directly any of the metal d orbitals. Instead, they approach to some degree in between metal d orbitals. These orbitals dxy, dyz, dzx are far apart by L by 2 from each of the ligands, where the two orbitals dx square minus y square and dz square are relatively far apart by L root 2 by 2, where L is the length of each side of cube. This indicates that ligand come closer to orbital directed to edges of cube than to those directed to the center of cube. So dxy, dyz, dzx orbital of metal cation experience more repulsion from ligands and are of higher energy than those of dx square minus y square and dz square orbitals. To maintain the rule of center of gravity, the orbitals dx square minus y square and dz square are 0.6 del t below the barycenter, and dxy, dyz and dzx are 0.4 del t above the barycenter. The G subscript is not used with T2 and E because tetrahedral complexes has no inversion center. This is the crystal field splitting in tetrahedral field. Here, firstly, degenerate d orbitals are shown. When ligand approaches to metal cation, so the degeneracy is break. Here, d orbitals are split into two sets dxy, dyz, dzx, referred as T2, and dx square minus y square, dz square, referred as E. Crystal field splitting in tetrahedral complexes is smaller than that of octahedral complexes because there are 2 by 3rd ligands of octahedral complexes and none of ligand approach the metal d orbital. For the same metal ligand and metal ligand distance, it is observed that del T is equal to 4 by 9 of del O. Factors affecting the magnitude of del O. First, oxidation state of metal cation. Higher the oxidation state of metal cation, greater will be the magnitude. Second, nature of ligand. The ligand which causes small degree of splitting of d orbital are called weak field ligand, and ligand which cause large splitting are called strong ligand. This order is called spectrochemical series. This order is written in increasing order, where I negative is less than Br negative, less than S2 negative, less than SCN negative, then Cl negative, N3 negative, F negative, weak OH negative, C2H5OH, then C2O42 negative, less than O2 negative, less than H2O, less than NCS negative, GLY, NH3, PY, SO32 negative, less than NH2OH, less than BPY, less than phenol, less than NO2 negative, less than CH3 negative, less than C6H5 negative, R3P less than Cn negative, less than Co. Number of ligands. The magnitude of crystal field splitting increases with increase in number of ligands. Principal quantum number of d orbitals. On moving from 3d to 4d, 4d to 5d, the size of d orbital increase and electron density decreases in them. So ligand can approach metal cation with larger d orbital more closely. Crystal field stabilization energy in octahedral complexes. It is given by minus 0.4 into T2G electrons plus 0.6 into EG electrons. So for D1, CFCE comes to be minus 0.4 del O. For D2, CFCE comes to be minus 0.8 del O. For D3, CFC comes to be minus 1.2 del O. For D4, minus 0.6 del O. For D5, for D4 low spin complexes, CFCE comes to be minus 1 del O plus P, 1P, which is pairing energy. For D5 high spin complexes, 0 del O. For D5 low spin complexes, minus 2 del O plus 2P. For D6 high spin complexes, minus 0.4 del O. For D6 low spin complexes, minus 2.4 del O plus 3P. For D7 high spin, minus 0.8 del O. For low spin, minus 1.8 del O plus 3P. For D8, both high spin low spin, minus 1.2 del O. For D9, only one configuration, minus 0.6 del O. For D10, only one configuration, 0 del O. Now CFCE, crystal field stabilization energy in case of tetrahedral complexes. It is given by minus 0.6 into E electrons plus 0.4 into T2 electrons. So for D1, minus 0.27 del T. For D2, minus 0.54 del T. For D3, minus 0.36 del T. For D4, minus 0.18 del T. For D5, 0. D6, minus 0.27 del T. For D7, minus 0.54 del T. For D8, minus 0.36 del T. For D9, minus 0.18 del T. For D10, 0. Hence, tetrahedral complexes only forms high spin complexes. Application of CFC, prediction of spin state. CFC helps to decide whether a complex will high spin or low spin depending upon pairing energy or crystal field splitting. If crystal field splitting is more than pairing energy, low spin complexes are formed. If crystal field splitting is less than pairing energy, high spin complexes are formed. Explain color of complexes. Color arises from DD transition between T2G and EG levels. Higher CFCE. Large del absorbs shorter wavelength, hence deep color is formed. Magnetic behavior. CFCE predict the number of unpaired electrons, so FeCN6 4 negative is diamagnetic due to strong field, high CFCE. Stability of complexes. Complexes with higher CFCE are more stable because more electron occupying lower energy T2G orbital, so greater is the stabilization. Among octahedral complexes, D3 is the stablest, then low spin D6, then D8 have highest CFCE, hence they are generally more stable. Preference of octahedral versus tetrahedral geometry. CFC can predict whether a metal will prefer octahedral or tetrahedral. For metals D3, D8, del O gives much larger stabilization than del T, so they prefer octahedral geometry. Hydration enthalpy of ions. CFCE contribute to hydration energy. Higher CFCE gives hydration higher enthalpy, so more exothermic reaction. Example, D3 ions like CH3 plus have higher hydration enthalpy due to large CFCE. Limitation of crystal field theory. It consider only the metal d orbital and sp orbital are ignored. This theory has not considered the covalent character in transition metal complexes, so CFT also has not considered pi bonding in complexes. CFT cannot explain the relative strength of ligand in given spectrochemical series. The compounds like NiCO4, in which metal is in zero oxidation state, ligand is neutral and have no electrostatic attraction between metal ligands. John-Tauler distortion. John-Tauler effect describes the geometric distortion of non-linear molecules in certain electronic state, which reduce their symmetry and lower their energy. This effect is named after scientists Hermann John and Edward Teller. This distortion is typically observed in octahedral complexes where two axial bonds can be shorter or longer than those of equatorial bonds. Octahedral complexes of D9 and high spin D4 generally show John-Tauler distortion. Two types of distortion is generally observed: elongated octahedral, compression octahedral. First is elongated structure, where A is the length between metal and ligand of which are in z axis, and E is the length between metal and ligand in x and y axis. So here A is greater than E. In the same way, distorted structure is that where E is greater than A. Static and dynamic John-Tauler distortion. Some complexes show tetragonal distortion under all conditions. This distortion is called static John-Tauler distortion. In these complexes, the splitting of T2G and EG orbital is quite high, so that thermal energy available will not be sufficient to affect the population of orbitals in distorted geometry. This type of John-Tauler distortion is strong and permanent. In some complexes, no distortion can be detected at room temperature because the direction of distortion randomly moves among available symmetry axes of complex more rapidly than physical measurement. In these complexes, the thermal energy available at room temperature cause equalize the population of complex signed in tetragonal elongated and tetragonal compressed average structure with no or weak distortion. This is called dynamic John-Tauler distortion. Application of John-Tauler. Prediction of bond length inequality. In experimentally determined structures, some metal ligand bond appear longer or shorter. For example, CuH2O6 2 positive, two axial CuO bonds are longer than four equatorial bonds. John-Tauler distortion explains these non-equivalent bond length by linking them with orbital degeneracy and electron repulsion patterns. Stability difference among oxidation state. Some oxidation state exhibit strong John-Tauler stabilization, making them more common or more stable. CO2 plus D9 is more stable than Cu plus in many complexes because D9 gains John-Tauler stabilization. Gowan's tetragonal distortion in complexes. The commonly observed tetragonal elongated octahedra in CO2 plus complex arise solely due to this effect. Without John-Tauler theory, the reason for these elongated structure would be remain unexplained. Helps in determining coordination number in some complexes. Sometimes a complex is expected theoretically to 6 coordinate but experimentally 5 coordinated because axial becomes extremely long. Ligand field theory. Crystal field theory has treated ligands at point charges or dipole and does not take into account the covalent bonding in complexes. Instead, it regards the bonding purely ionic. The physical measurements such as electron spin resonance or electronic paramagnetic resonance, nuclear magnetic resonance, nuclear quadruple resonance, and Rach parameter calculation from electronic spectra gives evidence in favor of covalent bonding in coordination compound. The covalent bonding in complex have been explained by ligand field theory. According to it, covalent bond between metal and ligand are formed by linear combination of metal orbital and ligand group orbital. Symmetries of ligand group orbital must match the symmetry of metal atomic orbital such that there is positive overlapping of LGOs with metal orbital along the bonding axis. Sigma bonding in octahedral complexes. In octahedral complexes, the ligand are approaching the metal cation on XYZ axis. Therefore, LGO will overlap with metal orbital along the octahedral bonding axis to form pi bonds. The metal cation has its valence shell 1ns, 3np and 5n-1 d orbitals. The octahedral symmetry has transformed s orbital into a1g, p orbital into t1u, dxy, dyz, dzx orbital into t2g, and dx square minus y square and dz square orbital into eg sets. Metal orbitals: s a1g, px py pz t1u, dxy dyz dzx t2g, dx square minus y square dz square eg. Since A1G orbital is spherically in shape, it can overlap with LGOs on all the axes. The T1U and EG orbital are pointing along the axis, therefore these orbital can form pi bonds on octahedral axis by overlapping with LGOs. The T2G orbital lie in between the axes, therefore these orbital are not capable of overlap with LGO to form sigma bonds. Therefore, out of 9 metal orbitals participate in, only 3 participate in pi bond formation. The T2G orbital are considered to be non-bonding molecular orbital in octahedral complexes where there is no possibility of pi bonding. If ligand and orbital of same symmetry, that of metal T2G, then T2G orbital will involved in pi bonding. Now the question arises that whether LGO and how are they constructed, each of equivalent atom contribute an atomic orbital or hybrid atomic orbital to form pi bonds. In octahedral complex, the 6 atom or hybrid orbital of 6 ligand are pointing along plus x minus y plus y minus y plus z minus z axis, which have been represented by sigma x, sigma minus x, sigma y, sigma minus y, sigma z and sigma minus z respectively. Pi bonding in octahedral complexes. In addition to metal ligand interaction, many ligand have orbital with pi symmetry with respect to octahedral axis and are capable of pi bonding interaction with metal atom. The pi bonding will significant if metal and ligand orbital have proper pi symmetry, comparable size and energy. The metal and ligand orbital involving pi bonding are perpendicular to ML axis. In an octahedral complex, there are 12 ligand group orbital capable of pi interaction. These LGO belong to 4 symmetry classes T2G, T1G, T1U, T2U. On the other hand, transition metal cation in octahedral has 2 type of orbital which are of correct symmetry for pi bonding. T1G, T2U ligand group orbital are non-bonding because there are no metal orbital of these symmetry. The metal orbital of T1U symmetry are directed along the axis of ligand, therefore involve pi bonding. Therefore, these orbital are unavailable for pi bonding. The T2G ligand group orbitals and metal orbital of same symmetry can form metal ligand pi orbitals. The bonding molecular orbitals are of lower energy and anti-bonding are of higher energy than atomic orbitals. Both bonding and anti-bonding molecular orbital are triply G. This diagram shows the pi bonding in octahedral complexes. Sigma bonding in tetrahedral complexes. The procedure for constitution for molecular orbital diagram for tetrahedral and square planar complexes is same that of applied for octahedral. The metal atom or ion in each case uses its 9 valence orbitals available for bonding, but symmetry properties are different from each geometry. For a tetrahedral Ml6 complex, Ml4 complex, the metal S and P orbital have A1 and T1, T2 symmetries. The dxy, dyz, dzx orbital have T2 and dx square minus y square and dz square orbital have E symmetry. It is seen that symmetry of P orbital and that of dxy, dyz and dzx orbital are identical. It is due to the fact that P orbital hybridized with S orbital and dxy, dyz, dzx orbital hybridized with S orbital form tetrahedral geometry. Of the 4 ligands constructed from ligand lone pair orbital have only A1 and 3A2, 3T2 symmetry. The A1 orbital LGO interacts with A1 orbital of metal to give one bonding, one anti-bonding MO, and T2 LGO can interact with both set of T2 orbital of metal to give one bonding and two anti-bonding molecular orbital diagram. In contrast to octahedral complex, metal E orbital are non-bonding. Separation between E and next T2 orbital is equal to del T as in CFT. For such complexes like COCl4 2 negative, there are total 15 valence electron of which 8 are produced by 4 ligands, and CO2 plus ion furnishes 7 electron. Either electron are filled in bonding molecular orbital and 4 electron in non-bonding E orbital and 3 in slightly ending anti-bonding T2 orbital. MO diagram for pi bonding in tetrahedral complexes. Sigma bonding in square planar complexes. In square planar complexes, the d orbital have A1g dz square Eg dyz dzx, B2g dxy and B1g dx square minus y square symmetries. The p orbitals have A2u pz and EU pxy py symmetry. Four ligands lying along the x-axis give rise to ligand group orbital of 1 A1G, B1G and EU symmetries. These LGO interact with metal orbital of same symmetry sigma molecular orbital. The A1G LGO interact with both A1G metal orbital to form bonding A1G and one slightly anti-bonding and one anti-bonding molecular orbital. The metal orbital B2G, EG and A2U remain non-bonding because they have no symmetry similar to LGO. In general, the square planar complexes are formed by D8 metal ions like Ni2 positive with strong ligand like Cn negative, Pd2 plus and Pt2 plus. There are 16 valence electrons, 8 from the 4 ligand and 8 from metal ion. 8 electrons from ligand occupy the bonding molecular orbital and 8 electrons from metal ion occupy B2G, EG and A1G molecular orbital and complexes are diamagnetic. Square planar complexes are highly stable though they contain 16 valence electrons. This is due to the reason that all bonding molecular orbital are filled and anti-bonding molecular orbital are empty. Adding additional electron would destabilize the complex because the additional electron would enter the anti-bonding molecular orbital and lower the bond order. The complexes containing electron less than 16 are also less stable because they have less number of electron in bonding molecular orbital and lower bond order. This is the molecular diagram for sigma bonding in square planar complexes. Thank you.